We will see the DC harmonic analysis by using one circuit. It's called a full wave rectifier with P circuit. You know rectifier, full wave rectifier. So half wave rectifier means what? It will just give, what is the rectifier means? AC to DC, right? It is called a rectifier. Whatever you give sinusoidal in the input, output, you will get the DC. At the output, you are not going to get like a pure DC immediately. The rectifier output may be like this. And also it's depending upon the rectifier circuit you are using in your system. So half wave rectifier means it will conduct only half cycle, and then another half will be cut off, and then another half cycle, and then another half cycle. Full wave rectifier means it will convert, this is the AC signal, right? You are giving like this. So it will convert positive cycle and also negative cycle into the positive side. And similarly here, positive to positive, and then the negative, we will also make it like this. So that is a full wave rectifier. So full wave rectifier, this is the output of this full wave rectifier circuit. Here we are getting DC component. Remember, this is AC to DC conversion. So we are only after this DC component, we are getting this output voltage. And we have the fundamental component, that is the sinusoidal wave. Based on this fundamental component, so many higher order harmonics are happening. Why I say these higher order harmonics are based on this one? Because the frequency is twice as this one. This is second order. If I have a third order, then third order will be at thrice, 3 times as the fundamental one. Okay, so this one we already know that from the previous slide. So here in this output, we want only A naught. That is the DC component. That is the DC output. Because we want only constant DC output voltage at the output of this rectifier. Rest of the AC harmonics are undesirable. So we can represent this waveform in terms of Fourier transforms or Fourier series. Let's say this is the waveform we had seen. Now we can represent this waveform in Fourier series. How can we represent? So V naught of t is equal to A naught, that is the fundamental DC component, plus sigma n is equal to 1 to infinity A suffix n cos n omega t plus B suffix n times sin n omega t. And now we can rewrite this equation like this. A naught plus the same sigma n is equal to 1 to infinity Cn times sin n omega t plus pi n. So here new constant, it's called Cn. Cn is equal to square root of an square plus bn square root of. And here pi is equal to tan inverse an divided by bn. So this is an divided by bn. So these are some standard formulas that you have to remember. There is no shortcut for this. So now let us expand this equation. Let us expand this equation for output voltage V0 of t or Vo of t by using different values to n. So here n is equal to 1 to infinity, right? It means you can apply the n value different values. First I apply 1, then I get A naught is just A naught plus C1 sin 1 omega t plus pi 1 plus what is the second value? Because here n is equal to 1, 2, 3, 4 and so on up to infinity. So now I apply 2, then it's becoming like this: C2 sin 2 omega t plus pi 2, C3 times sin 3 omega t plus pi 3 plus and so on. So as I already told you, here we had seen the component. Here we have a constant. This is the RMS value. So here now we have to find RMS value of each component. We know that there is a DC component and there is a fundamental component and there are higher order harmonics components. Each component has its RMS value. A0 is the RMS value of this DC component, and C1 divided by square root of 2, that is the RMS value of this fundamental component. C2 divided by square root of 2, that is the RMS value of this second order harmonics component, and so on. So we are having here square root. Remember this, that's why we call this as a root mean square value. Okay. So here RMS value A0 is the desirable one because this is AC to DC converter and others are not desirable. So we want only this A0 and we do not want this, we do not want this, we do not want this. But output, at the output, we have everything together. So square root of A0 square plus 1 by 2 times C1 square plus C2 square plus C3 square and so on. I am just applying everything and then I am making this RMS value of the output voltage. I know RMS value of each component, so now I'm making the total RMS value of the output voltage. And now I just rearrange this equation. So now it will become square root of VO RMS square minus A0 square equal to this rest of the components which are under this square root. Remember, this is not really needed. These are undesirable. This is called harmonic components, higher order harmonics. But anyway, it's coming here as the output. Since we are doing the Fourier analysis, Fourier transform analysis, so we are just only after the terms, mathematics. Okay, so now square root of VO RMS square is minus A0 square is equal to the same equation. Let us call this as a equation 1. I am bringing the same equation here, equation 1. Okay, I have the number equation 1 here, so this may be equation number A. So I call this component, this entire harmonics component with a single letter called VOH. So we can call this VOH as a harmonic voltage. So the value of the harmonic voltage is square root of 1 by 2 times C1 square plus C2 square plus C3 square plus C4 square and so on whole square. Okay, this is equation 1. So now you should know VOH is equal to total voltage minus desirable voltage. So we get an equation for harmonic voltage. Now, because of the Fourier transforms, we found the equation for this undesirable harmonics voltage. So VOH is equal to total output voltage minus desired output voltage. So we will just see one number with the example. Let us say I am applying 1 volt as the input. At the output, I am getting maybe 5 volt at the output. I am expecting the same 1 volt here at the output, but I am getting this harmonics. So output voltage is equal to 1 volt plus 4 volt, right? So this 4 volt is the harmonics and this 1 volt is the desirable fundamental, or this is the DC component here. So if I want to, okay, this is called harmonics and this is called the desirable voltage. And this is the total, I'm talking about this 1 volt is the desirable voltage. This 4 volt is the harmonics. This 5 volt is the total output, TO. Or we can just say like VTO, that is the total output voltage. So V total output voltage is equal to, so now we have the desirable voltage dV plus harmonics voltage is HV. 1 plus 4 equal to 5. Now I want to find out only the harmonic voltage. Then what should I do? HV is equal to VTO minus desirable voltage. So 5 minus 1, that is 4. That is what? This harmonic voltage. The same thing we are using here, the same logic. Harmonic voltage is equal to total output voltage minus desired output voltage. Everything is in terms of RMS values. So we know this equation now. So now we divide this the above equation by A naught in both sides. In both sides we divide by A naught, so we can rewrite the same equation like this. So VOH divided by A naught is equal to square root of VORMS divided by A naught whole square minus 1. This is important equation number 2. So remember these equations, or note down these equations. So remember, based on these equations, 2 equations, we can derive few more equations. That is what we are going to do in this slide. So we already know this one. This is the VORM, this is the harmonic voltage VOH. And after we divide this entire equation by A naught in both sides, then the equation becomes like this. So this VOH divided by A naught, it has a name. It's called voltage ripple factor, VRF. So VRF is equal to VOH divided by A naught. This is the harmonic voltage and this is a desirable output voltage. And we have another formula called form factor, FF, is equal to VORMS divided by A naught. VORMS means what? Is a total output voltage divided by desirable output voltage. So please remember the meaning of each term. Then you will understand the meaning of this formula. So VOH means that is the harmonics, unwanted one. A naught, that is the wanted or desired one. And VORMS is the total voltage, output voltage. That is harmonics plus desired voltage. Okay, so now we can consider 2 cases. Case 1. If there is no harmonic, then we will get a pure DC output without any distortion. That's perfect, right? So we do not have any distortion and we are getting pure DC output. So now what will happen to these formulas? So now VORMS is equal to A naught. So the total output voltage is equal to RMS value of the desired DC voltage. Right? RMS value of the total output voltage is equal to desired voltage. That is what happening here. We know the equation for the total VORMS. Where is VORMS? Do we have VORMS? So after we rearrange here, it's like this. But we know VORMS means what? VORMS means that is the total voltage. That is what I represented with this one, VTO. VORMS is equal to desired voltage plus harmonic voltage. If the harmonic is 0, then VORMS is equal to desired voltage. That is what given here. And VOH harmonics, we assumed it's 0 if no harmonics. It means we assumed harmonics is equal to 0. VOH is equal to 0. Total harmonics is nothing. And VRF is equal to 0. What is the formula for VRMS? VRF, that is a ripple factor. Ripple factor formula is VOH divided by A naught. VOH is 0 means then this is going to be 0. VRF is equal to 0. Naturally, it becomes 0. And what is the form factor FF? The same formula, VORMS divided by RF. So here we already we found the formula called VORMS is equal to A naught. So here I apply this VORMS is equal to A naught. Then A naught cancel. So then it will become 1. So that is form factor. Form factor is equal to 1 for this case. Since A naught is equal to VORMS, then FF is equal to 1. This is the perfect case. And the case 2. Now, if there is a harmonic in the output, of course, output voltage will get distortion. So what are the conditions for having this kind of situation at the output? So here we already have the formulas. So now the total output voltage. Total output voltage is greater than the desired voltage, right? So we will go to this example again. So the total output voltage is greater than the desired voltage, because now total output voltage is 5 volt, but we want only 1 volt as the desired voltage at the output. So this 5 volt is greater than this 1 volt. That is what I mentioned here. VORMS is greater than A naught. Now VOH is greater than 0. It's obviously because total harmonics is not equal to 0, then VOH is not equal to 0. VOH is more than 0. It means we have a harmonic, that is some value. VOH means it's a harmonic, right? So its value is 0 because we assumed there is a harmonic. And VRF, this voltage ripple factor is greater than 0 because we apply some value here, and A naught there is already some value, so there is some number. So definitely this VRF is greater than 0. It's not equal to 0 like this case. And FF form factor is also greater than 1. What is the formula for form factor? So here is a form factor. So VORMS, total voltage divided by A naught, that is definitely not equal to 0 or not equal to 1. It's greater than 1. So that's all about DC harmonic analysis. So what we had done in the DC harmonic analysis, so here we did not really find a solution. How can we avoid the harmonics? Here just only we are doing mathematical analysis. So we represented the waveform in terms of Fourier transforms, and we found the total RMS output voltage, and then we just make the equation for harmonics only, and we are dividing this divided by desired voltage in both sides. Then we get this one, and this is called voltage ripple factor. And we also have another one. This is the harmonics divided by desired voltage, and form factor is total voltage divided by desired voltage. We are handling everything in terms of RMS. And here we applied 2 cases. Case 1, no harmonics. Then these are the conditions. If you do not want to have any harmonics in your output, if harmonics happens, then this is the formula, and this is what happening. So remember these equations. Maybe we need all these equations when we study rectifier circuits.